So, closing remarks. Computing problem is a language, a set of finite binary strings. To solve computing problem with an algorithm is to produce a Turing machine M which decides L. Decides means if a string is in L, the Turing machine halts and says yes. If a string is not in L, the Turing machine halts and says no. One final minor detail, which is going to be very useful later on, which is the concept of an encoding. So you built your fancy Turing machine. You call up your friend in California and you say, look at my fancy Turing machine. And it's a telephone and you can't look at it. Okay, we didn't have FaceTime and stuff in the 50s. Okay, so how are you going to tell your friend about this fancy Turing machine that you have built over the telephone? Okay, you can't, he can't see that fancy image with graphs and edges and labels and so on. Okay, so what you will do, okay, so describing a Turing machine, describing a Turing machine M. What you will do is you'll say, listen, buddy, I've got states. Okay, so for example, Q0, Q1, Q2, and so on. And then you'll say, listen, I've got this infinite tape thing that we discussed in Fox. It's called a Turing machine. And on this tape, the following kinds of symbols can appear. So you'll tell him what the symbols are. Okay, and the default symbols for us are the star, the space, the punctuation, 0 and 1. Okay, and that suffices. We don't need many more symbols. Okay, check marks and so on. Those are useful too. Okay, and then you have to tell all the instructions. So you have to tell all the machine instructions. So let's remember what a machine instruction looked like. There was an initial state, okay, and then, what you read, let's say 0, and then what you write, let's say 1, and then which way you move, let's say you move left, and then what state you transition to. So let's say you start in state Q1, you transition to Q3. So such an instruction you can represent as a sort of 5-tuple. Q1, 0, 1, L. So read 0, write 1, move left, and then transition to Q3. Okay, and each such instruction in your Turing machine will be some such 5-tuple. Okay, and then when all is said and done, you can take these states, construct them into concatenate them into a string, then concatenate onto that string the symbols, and concatenate onto that big huge string the machine instructions, and at the end of the day, you can convert this into one humongous string. So convert it into a string of bits. And that's no surprise to you. So for example, when we communicate now electronically by email or by voice over IP, we take some signal and convert it to bits and send this huge bit string across the internet, across your bandwidth. Okay? And so what this means is that any Turing machine can be described without any ambiguity by a string of bits. So a Turing machine M can be described by a string of bits. And so what you can do when you're talking to your friend is you send your friend this string of bits, the friend gets the string of bits, and then, decodes it into, whatever the states are, the symbols, and the instructions. Okay. So when you take a Turing machine M and you describe it by its string of bits, we call that the encoding of M. Okay. And we write that as the encoding of M. In fact, you can encode anything. You can encode a graph into a string of bits. You can encode a set. Anything you want. Any object you can encode. Because at the end of the day, we describe things with zeros and ones in computers. And that's the encoding of any object. In particular, you can encode a Turing machine into a string of bits. Okay. So every Turing machine corresponds to a unique unique string of bits. So what does that mean? Okay, so that's going to be a very useful concept, the encoding of a Turing machine into a string of bits. But already we hint at something that's unfortunate. So we have deciders. Let's say Turing machines M1, M2, M3, and however many Turing machines we have. Okay, all the Turing machines you can draw. Well, they all can be encoded into their corresponding string of bits. and so on. Okay? You can think of this as, the language of all possible Turing machines. Okay? All possible strings of bits that correspond to Turing machines. And any given string of bits corresponds to just one Turing machine. Okay? And any Turing machine corresponds to its corresponding string of bits. Well, when we started this module on the theory of computing, we said that the number of finite binary strings, well, not number, but the cardinality, the set of finite binary strings is countable. So, set of finite binary strings is countable. That means, since the Turing machines are just a subset of the finite binary strings, the Turing machines are countable. They can be listed. Okay. So the Turing machines are countable. In fact, you can list them. There's a first Turing machine, the simplest, and the second Turing machine, and the third, and so on. So there's the first Turing machine, and the second Turing machine, and the third Turing machine, and so on. Wow. Okay. Turing machines are countable. They can be listed. There's a deep consequence of that. Since the Turing machines are countable, and that's what corresponds to an algorithm, okay, that's the Church-Turing thesis, it means that since computing problems are uncountable, it means that there are computing problems that can be defined, but for which there is no Turing machine that solves them, because there are way more computing problems than Turing machines. Okay. It means that there are computing problems for which there is no algorithm that solves them. There are many such problems. In fact, there are uncountably many computing problems which cannot be solved by a Turing machine, which cannot be solved by an algorithm. And that is period. Okay. And so we call these problems unsolvable. In particular, we call them undecidable, because we're only interested in Turing machines that are deciders. And if there's no decider to solve a problem, we say it's undecidable. Okay. And so the next lecture is going to be about, can we find some important problems and show that they are undecidable, that they cannot be solved? Next time. Checking out.